So good evening everyone. Today is our lecture 6 of NPTEL course, NPTEL TA for the course Algebra-I, and so this week's content was introduction to ring theory and some ideal and uh, maybe homomorphism and things. So okay, so we'll be doing some problems related to general ring theory and some problems related to homomorphisms and everything. So start with our first problem, that is okay. So first let us say this is lecture 6 and the contents are ring theory and everything, and let us say that we are R denotes as ring, maybe with identity, but anyway. Okay, so start with our first problem. If every element x of R satisfies x square equals to x, prove that R is commutative. Now note that you can say this as remark: a ring in which x square equals to x for every elements x of R is called a Boolean ring. So these kind of rings are important in discrete math, especially in number theory, combinatorics, computer science, graph theory. Okay, so maybe we start with the solution. Now we are given x square equals to x for every x belongs to R. So x square equals to 0 implies x equals to 0, right? As x square equals to x. But we have for every xy of R, xy minus xyx whole square equals to xy minus xyx dot xy minus xyx. So this would imply that xy dot xy minus xy dot xyx minus xyx dot xy and plus xyx xyx, and this xx in the middle implies x square, right? So this implies this is x, and again here this x square implies this equals to x and this equals to x. So if I write down this would imply that xy minus xyx minus xyxy plus xyyx, sorry, xyxyx. So you see that this cancels this and this cancels this, so this is 0. But xy minus xyx whole square equals to xy minus xyx, right? Because x square equals to x for all x. So from the previous proof we have this, and similarly we can see yx minus xyx whole square equals to 0. Therefore yx minus xyx equals to 0. And I mean, if you note this by 1 and if you note this by 2, now using 1 and 2 we see that xy equals to xyx equals to yx. This implies xy equals to yx, which for every xy belongs to R. Hence R is a commutative ring. So this proves our first theorem or first exercise. Now we come to our second problem. That is, if D is an integral domain and D is of finite characteristic, okay, so D is of finite characteristic, prove that characteristic of D is a prime number. Now note that what is an integral domain, that integral domain is a ring, or you can say that it is a commutative ring, where if product of two elements is 0, then either one of them has to be 0. So I think it will be the one of the central objects of study in your remaining course. So I thought maybe doing a problem this is a good idea. So let us solve this. So you can think that let the characteristic of D is P. P is a number, not necessarily prime. Therefore, we have that P dot A equals to 0. For every A belongs to D, and say that P is the smallest such integer. So it is possible, right? Because uh, P is a positive integer, so it has a lower bound. So since P has a lower bound, so we can think of smallest of those numbers, that is the lowest minimal you can say it as minimal lower bound, or like minimal number. Now one thing to note, that when A is non-zero, then P cannot be 1, right? Because if P is 1, then A equals to 0, which contradicts to our assumption that P cannot be 1. So now P not equals to 1 when A is non-zero. So P can be anything, any positive integer. So suppose, let's assume that P is not prime, because we want to prove that P is prime. So if we assume that P is not prime, then let us see what happens. Suppose P is not prime, therefore P equals to RS for some positive integer R and S, with such that R and S are both not equals to 1. Now since A belongs to D, now we have A square belongs to D2, so we have P dot A square equals to 0, right? Because P dot A equals to 0 for every A of D, so A square belongs to D, so this is also true. We can write it as RS of A dot A equals to 0, and this implies that RA dot AC equals to 0 from the distributive property. Actually what is happening here is that you are taking A square RS times, like adding RS times. So if you just take like RA first, then take SS later, then you can rewrite this in this form. Now D being an integral domain, implies RA equals to 0 or SA equals to 0, right? When RA equals to 0, we have for every A belongs to D, we have for every X belongs to D, RA of AX equals to 0. So this implies that A plus dot dot A, say R times X equals to 0, and this implies AX plus AX to AX equals to 0. It is also R times. So this would imply that A of AX plus X plus up to X R times equals to A of Rx equals to 0. But your A is non-zero and D is an integral domain. Therefore, one implies Rx equals to 0. So we have that your X was arbitrary. So we have Rx equals to 0 for every X belongs to D with 1 R P. Because your P was minimal and R is not 1, so this is a contradiction to the fact that you took P as the smallest positive integer. Similarly, if you take SA equals to 0, you have a contradiction. So thus you cannot have such an integer as a smallest integer which is not prime. So this implies that P has to be prime. So if I write this down, so this implies that it's a contradiction as P is the smallest such integer. Similarly, when SA equals to 0, we have contradiction thus P equals to RS is not possible, thereby P is prime. So we have done our second proof. Now coming to the third proof. So it's an important it's an interesting exercise. Give an example of an integral domain which has an infinite number of elements yet is of finite characteristic. So what I'm saying is that we have to find an example of an integral domain which has to be in which has to be of finite characteristic, but its cardinality has to be infinite. So we can think you can think this for 2 or 3 minutes. If not, then we will try. Okay. So let us prove this one. So you know that ZP is the uh, ring of integers modulo p. So I better write this as p modulo p. So this is a ring of integers when p is a prime, then
ఏంటి
ZP
ఆ,
is an
8కి అయిపోతుంది ఫోన్ చేయరాదు
integral domain
శ్రీకాంత్కి ఫోన్ చేయరాదు
uh, So then ZP is an integral domain with finite cardinality, obviously, and it is also a field. But anyway, now we define ZP so now we define ZP of AX equals to AM x to the power m am minus 1 x to the power m minus 1 plus a1x dot a0, right, where your ai goes to ZP and m obviously belongs to the whole numbers, that means natural numbers with 0, where ZP is a field of integers modulo p and p being prime. Now clearly p of fx equals to 0 for every fx belongs to ZP of x, right? Because this will become 0 mod p. Also, if you notice carefully, ZPX has infinite number of elements, right? Because I mean, you can think that this is spanned by 1x square to this, and obviously this is a as ZPX is a vector space, is an infinite dimensional vector space over ZP, a field. So as it has infinite dimension, so obviously it has infinite elements. The next question is also a interesting one. If D is an integral domain and if NA equals to 0 for some A not equals to 0 in D, and obviously and N not equals to 0, prove that D is of finite characteristic. I mean, you are given that this is true for some elements, and note that the definition of finite characteristic means that there exists some n not equals to 0 such that na equals to 0 for every a. So there is a difference, and it says that if it is true for some elements, then it is true for every elements. So I'm going to give you 1 or 2 minutes so that you can think, then we'll be doing this. So uh, we are given n equals to 0 for some a belongs to D with a not equals to 0 and n belongs to capital N. We have for every x belongs to D, na of x equals to 0. So this implies that a plus a x equals to 0, and this implies that ax plus ax to ax equals to 0. Now if you suck a out, then you will see that 2x, and note that this is n times, right? Because it follows from the first line, that so this implies that a dot nx equals to 0. But we have a not equals to 0 and D being integral domain. So if I note this by 1, so 1 implies nx equals to 0 and your x was arbitrary, right? For every xd x belongs to D, you manage to show that nx equals to 0. So we have nx equals to 0 for every x belongs to D. This shows that D is of finite characteristic, right? Now we can do some problems related to ideals and field and some homomorphism. Okay, so let's start with some trivial question, which is if U is an ideal of R and 1 belongs to U, that is identity element, prove that U equals to R. So again you can just think for some minutes, so then I cannot also take time to think this one, and you also think and let me know. So yeah, let us think this. Now, for every small u belongs to u and small r belongs to capital R, we have ur belongs to u. So, if 1 belongs to u, we have 1 dot r equals to r belongs to u for every r belongs to r, right? So this implies we have r belongs to u, but u belongs to r, so we have u equals to r. Now following this, we are going to prove a string of theorems following this direction. If f is a field prove its only ideals are 0 and f itself. So what is a field? If you don't know, that field is a commutative ring, or it's better if you a field is an integral domain where every non-zero element has an inverse. So this means that if you take any non-zero element from a field, it will have an inverse in them. So field is the ultimate uh, uh, algebraic structure or algebraic set we desire. So so the exercise says that if you are given a field, then it has only trivial ideal. It has no non-trivial ideal. So again we will assume that it has a non-trivial ideal, and so that it is not non-trivial. It cannot be non-trivial. So suppose u be some ideal of f. Now either u equals to 0 or u not equals to 0. Clearly e equals to 0 is an ideal of f, and it is trivial. So when u not equals to 0, there exists some a of u such that you have a not equals to 0, but a being a field, there exists a inverse belongs to f such that a dot a inverse equals to a inverse dot a equals to 1. Now A inverse dot A belongs to U, right? Because A inverse belongs to F and A belongs to U. So this implies that 1 belongs to U. So from the previous exercise, what we did that if U is an ideal and 1 belongs to U, then you have U equals to F, which is again a trivial ideal, which is again a trivial ideal. So we are done. Now following this, we are going to prove another interesting result. Prove that any homomorphism of a field is either an isomorphism or a trivial one. That means takes every element to 0. So that means zero homomorphism. So again you take some time to think about this, and then we will be doing this, and I'll be taking a break for 2 minutes. So let us solve this. Let F be a field and R some ring. Let, not let, just here, put it here, and phi from F to R be some homomorphism. Let K phi be the kernel of phi. We know K phi is an ideal of F, but the only ideals of F are 0 or F itself, right? So when K phi equals to 0, we claim phi is a one-to-one mapping. But this is true because from the isomorphism theorem of ring you can see uh, this is true. But this is true from the isomorphism more specifically first isomorphism theorem of rings. This says that F by kernel phi is isomorphic to image of phi, which is a subring of R, and since kernel phi is 0, so this implies that F is isomorphic to image, and obviously image sits as an injective object inside R. So this is true. And but when K phi equals to F, then phi of x equals to 0 bar for every x belongs to F, or that means similarly phi takes every element of F into 0. So we are done. The next one, it was 7. And it is 8. If R is a commutative ring, A belongs to R, A, show that A of R, A of R belongs to R is a two-sided ideal of R, and B, show by an example that this may be false if R is not commutative. So you can try this for 2-3 minutes, then we will again start.
Big and magical.
So let us start solving this. Uh, for the part A, first we will show AR is a subgroup of R. But this is simple because suppose x equals to AR1 and y equals to AR2 for some R1 and R2 of R. But then x minus y should be A of R1 minus R2. R1 minus R2 belongs to R because it is a ring. So x minus y belongs to AR. So thus small a capital R is a subgroup of R under addition next we are going to show that it is closed under scalar multiplication. Next, if sum x belongs to AR and R belongs to capital R, then we have R dot x equals to R of x, say suppose AR4 belongs to R. So this implies that since R is additive, you can just commute R and A and you get R4. So this again belongs to AR, right? So and similarly, if you take x dot R, you will be seeing that AR4 equals to AR4 dot R, and since again R is commutative, you can just write it as no need to change this AR4 dot R, and again this belongs to AR. So this shows that AR is a two-sided ideal. Now the second question was that show by an example that this may be false if R is not commutative, and you can see precisely where we used commutativity. Here, only here. So to show that it was a left ideal. So let us take an example. Consider R equals to second bracket A, B, C, D, the set of matrices where A, B, C, D, the entries coming from the set of integers. So this is an exercise you can do. R is a non-commutative ring. You got to show that there exist two matrices such that if we flip their positions in the product, they won't be equal. Now let A equals to 1 1 0 0. Again we can easily check that small a capital R equals to AB00, where your A and B are coming from Z. Clearly AR is not a two-sided ideal as for 1 1 0 0 of small a capital R and 1 1 1 1 from R we have 1 1 1 1 1100 equals to 1111 doesn't belongs to small a capital R. Thus, in a non-commutative ring R, small a capital R is not an ideal. So we are done. Okay, let us get introduced to two new kind of objects. One is called radical of an ideal, and second one is called annihilator of an ideal, or annihilator when u is zero, ideal is zero, but this is I'm forgetting the name, but anyway, so this should be 9. If u is an ideal of R, let R of u equals to x belongs to R equals to x of u equals to 0 for all small u belongs to capital U. Prove that smaller capital U is an ideal of R. So let us solve this. So again you can think for 2 or 3 minutes, and if you can do this, you can tell me so that I can also rest my mouth and hand. Oh no, this is not annihilator. Annihilator is something comes when you treat R as a module over itself, so better to not bring that term here. This has some name in Atiya commutative algebra. I'm just forgetting. Not this one. The next question I am about to ask. This one is called radical of an ideal. So nothing to worry about. Okay, I will go to the next question first, but let us solve this because there are some people who also like uh, see the recorded lectures. So you wait. First, let me do this, and then I will go to the next one. Okay, let some xy belongs to uh, R of u. Therefore, therefore xu equals to 0 for every u belongs to u, and yu equals to 0 uh, for every u belongs to u. Actually, you know what? You can say this Ru as an annihilator. There is no problem. Annihilator of u, annihilator ideal of u. You don't need to go to the next question. I'm using the notation wrong, so I read it wrong. You can say this Ru as better to let me Ru annihilator ideal of u. Okay, so yu for every u belongs to u, but then x minus y of u would be xu minus yu equals to 0 for every u belongs to u. So you have that x minus y belongs to R of u. Thus we have R of u is a subgroup of R under addition. Next, suppose some x belongs to Ru and small r belongs to capital R. Therefore, x dot u equals to 0 for every u belongs to capital U. We have small xr of u equals to x of Ru is equals to u1 for some u1 belongs to u. Therefore, xr of u equals to x of u1 is to 0 for every u belongs to u. Similarly, I mean so this implies that xr belongs to R of u, and similarly we can see R of x belongs to R of u. So R of u is an ideal of R. So we are done. And coming to your next question, that is, if U is an ideal of R, let equals to x of Rx belongs to U for every small r belongs to capital R. Now prove that capital R dot capital U is an ideal of R and it contains U. Now note that when we take uh, now let it it's okay. Okay, so you can try this for 5 minutes, and we'll start discussing this at 7:20. So I'm basically following Harstein. Uh, so if you have the book, you can open the exercise of ring theory. Uh, if you don't have the book, so I'm giving my hand some rest. I have been writing for almost 1.5 hours right now, so my hand is it's like it's causing pain. Okay, so let us start doing this. Suppose some xy belongs to R double dot u, therefore Rx belongs to u for every R and Ry belongs to u. Since u being an ideal, we have Rx minus Ry equals to R of x minus y belongs to u for every R belongs to R. So this shows that x minus y belongs to u. Thus dot u is a subgroup of R under addition Next, suppose small x belongs to this object and R1 belongs to R. Therefore, Rx to U for every small r belongs to capital R. Also, R of xr1 equals to Rx r1, which is u1 r1 for some u1 belongs to capital U, but capital U being an ideal, therefore u1 r1 belongs to U. So R of xr1 belongs to U for every small r belongs to R, implying xr1 belongs to for every r1 belongs to R. Again, R of r1x equals to R of r1x equals to r2x for some r2 of R. So R of r1x equals to r2x belongs to U, implying r1x belongs to U. So r1 of x belongs to r dot U for every r1 to R. Hence, is an ideal of R. Also, if small x belongs to capital U, therefore small small x belongs to U for every r to capital R, as U is an ideal of R. But small x belongs to U for every small r belongs to R implies small x belongs to capital R capital U. Thus U belongs to capital R capital U. So we are done. Next, let us do a problem. It's an interesting one. So, what can you say about the right intersection and left intersection of left right ideal and left ideal? If you intersect them, and what can you say about that? Again, you can try this for 5 minutes, and then we will start doing the solution. Okay, let us solve this. Intersection of a left ideal and right ideal of R need not be a left ideal or a right ideal. We substantiate our statement with an example. Consider M to Z equals to A, B, C, D. A, B, C, D belongs to Z. Clearly, M to Z is a ring. We define U1 equals to AB00. AB belongs to Z. And U2 equals to AB00. AB belongs to Z. Now check that U1 is a left ideal of M to Z and U2 is a right ideal of M to Z. Whereas U1 intersection U2 equals to A000 belongs to Z. Clearly, U1 intersection U2 is not a left ideal as for 1000 belongs to U1 intersection U2 and 1111 belongs to into Z. We have one 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 1000, so it would be 1010 belongs to U1 intersection U2. Similarly, U1 intersection U2 is not a right ideal as for 1000 belongs to U1 intersection U2 and 1111 is to Z. We have 1000 equals to 1100 section 2. So U1 intersection U2 is neither a left ideal nor a right ideal. So we are done. Okay. So let us stop here for the day, and for the next class we will have okay, let me see. So there are some again ring related syllabus and things. So okay, so everyone, good night.